Hello everybody, my name is Carlos, and today I'm going to talk about my presentation for our final assignment for our COT6930 class, Randomized Algorithms and Secure Designs, which I've titled Blockchain and the Revolution of the Gaming Industry. So this presentation, while I'm going to be mostly talking about the blockchain, I'm going to present it in the context of the gaming industry and how it can benefit it. For this, I have a few points that I'm going to mention, such as what are the current gaming problems in the gaming industry, then talk about a brief introduction to the blockchain, mention how the blockchain can help the gaming industry, then the math behind the blockchain, how it works, and basic implementations and algorithms for use, the mention of examples of blockchain-based games such as CryptoKitties, and last but not least, I will talk about the possible future with the blockchain, meaning what threats it may face and what uses it may be given. So with that, let's start. The current gaming problems in the gaming industry are as follows. Due to the rise of the gaming industry as a business, it is more common to find games which involve currency, be it from the game or money from the real world is able to be used in the game. And many times, in order to get valuable items, players are going to be inclined to either play a game for multiple hours in order to earn the in-game currency, or they can skip this process and pay real money for it. Because of this, we need to ensure that purchases are made securely so that there are no instances of fraud or losses in transactions. And we want to, through this, make sure that the rising trend of value for intangible assets is secure, but we also want to make sure that the purchases made in a game are not subject to any kind of fraudulent transaction, meaning interception or scams or any other sort. Aside from this, a game needs a safe environment in order to be able to be launched. Again, we want to emphasize the point that purchases need to be made securely, that the rules of a game and its continuity, its use, its popularity need to be constant and not subject to the current change, which we see right now when a game needs to be updated or rules are changed and there is little say to the players, as well as players who are really involved in a game cannot contribute to it. There is also the issue of if a game is too popular, it will be discontinued and another game takes its place and so on. But for each game, players have to create a new profile. Player profiles are not interoperable across games. And the same thing, if a player invests a lot of money in a game, they might spend real money or resources or time, and this time is not reflected on another game because their assets do not transfer to it. They start over. So now let's talk a bit about the blockchain. The blockchain, in simple terms, is a system of recording information so that hacking and changing becomes impossible or computationally infeasible, which is pretty much the same thing in terms of considering how much time and resources a hacker would have. It is basically a digital ledger of transactions which is copied and distributed across an entire computer network, meaning that all users get a copy of every transaction made in the blockchain, and every time a transaction is made, it's copied and added to every participant. This helps in the process of decentralization, where everyone using the blockchain is in charge instead of a single entity. Consider the uses of a game, for example, today, where there is a single server or a single game development agency which controls the game and has a say on what to add, what to do with it, which may frustrate players and discourage them from playing. Now, if the gamer has some form of say in what to do and how the game mechanics change, then it may be far more interesting. Some benefits that the blockchain also brings as a whole to any industry would be a transparency, because every participant shares a copy of the ledger and data becomes more accurate and consistent. Security, because transactions are encrypted and linked to the previous one, meaning that every transaction is linked, hence the name blockchain. Traceability, good exchanges are recorded and participants can count on an audit trail, because every transaction is linked to the next one, information about it that is consistent and can be read across all users. Efficiency, because of this record keeping, we eliminate the need for multiple ledger reconciliation and intermediaries. And because we eliminate the third parties and middlemen required to keep this record, we are decreasing our cost. So how can the blockchain help in the gaming industry? Through the blockchain, game purchases can be facilitated. We eliminate a third-party payment provider and their fees. Every time that we try to pay for something, there is always going to be a fee of a certain percentage of the purchase. And because we're paying for it and we have a clear notion of what it is and we share a copy of all transactions, we have a true ownership of our assets, and the value trend for an intangible item is validated and keeps increasing. This then becomes a safe and secure environment for developers, because there is no centralized server to attack. Everybody is going to have a say and is going to be in charge in the blockchain. Therefore, it becomes difficult or impossible to attack. We can store the in-game assets securely because of this, and it becomes a secure environment for developers because of the ease of tools that are being brought in order to develop with them, such as companies like Engine and Loom Network, which are developing their own tools. And we can have the option for interoperable player profiles. Players can take their unique public addresses across games and with them perform transactions. And this brings forward the smart contracts, which allow for rare in-game assets. So now let's focus a bit on the math that is behind the blockchain. How does the blockchain ensure the security over transactions recorded? Blockchain bases its transaction process on a public key cryptography scheme. Basically means that a message is encrypted using a public key which is known by everyone, and a private key, but the private key is kept by the user, hence the names. So an encrypted message cannot be deciphered with knowledge of the public key alone. Most cryptocurrencies today use what is known as elliptic curve digital signature algorithms, or ECDSA, which is a type of public key cryptography which depends on a 256-bit private key, which is obtained by the equation y squared is equal to x cubed plus ax plus b. Now, the cryptocurrency called Bitcoin and the environment Ethereum use an elliptical curve equation, which is a little bit different. In this equation, the a is equal to 0 and b is equal to 7. So we get the formula y squared equals x cubed plus 7. This type of curve is known as sec p 256k1, and is the one that you see on the right of the slide. So why is this curve important? It allows for the quick calculation of point addition. Now, point addition can be described as follows. On the curve, we have a point that we use as a base. If we draw a tangent through it, we'll stumble upon a second point. And if we do the opposite on the dotted line, we will get the double of that point. And that's how we perform an addition. Now, in numbers, if we have, for example, a number 6p, in order to be able to get 6p, we need to add normally p 6 times, and this requires 6 operations. But let's consider the use of a reverse of the distributive property, where we have n dot p plus r dot p equals to n plus r dot p. Basically, we can just group the p's and add the numbers that are multiplying them, such as in the example that we have 4x plus 2x, we simply know that that's 6x, but it also becomes 4 plus 2 times x equals 6x. So in the case of getting 6p, we can get first P plus P, which is 2P, then 2P plus 2P, which is 4P. Then by that formula, 4P plus 2P is equal to 6P. And that amounts to 3 operations. And that reduces the times that we have to add P in order to get, well, the point addition. So how is this important? If P is so easy to find, how is the blockchain formula secure? So the SecP256K1 algorithm for encryption and decryption is defined by the equation K equals X dot P, where each variable represents K being the public key, X being a private key, which is expressed in an XY coordinate because we're in the curve, and P being a base point along the elliptic curve. Considering that we're using 260-bit keys, the private key could be a number between 0 to 2 to the power of 255 minus 1. So that means on average, depending on where our key is, be it the middle, the center, or the end, we will have around 2 to the 128 calculations to perform, which is computationally infeasible to obtain. So regardless of this, if the XY coordinates used for the private key are too large, they may not be stored in the 256 bits. So the curve needs to be defined over a finite field. And in order to be able to get a finite field, we can use modulus operations. Let's assume a simple formula M equals P times Q. If we add a modulus operation to each side, having M mod n equals P times Q mod n, we're not affecting the result in any way. We're getting the same thing. So the traditional curve y squared equals x cubed plus ax plus b could be expressed as y squared mod p equals s cubed plus ax plus b mod p. So how do we express this better in order to be able to get the values that we need? We need to have smart contracts that are able to check if a user's signature is valid, and by that we need to check if they have the private key x. So let's consider again the reverse distributive property n.p plus r.p equals n plus r.p. If we add a hash function to both sides, considering that this hash function involves the modulus operation in some way, we will have hash of m comma r.p dot n.p plus r.p equals hash of n comma r.p dot n plus r.p. If we want to convert this into the equation k equals x dot p, we have the following. If k equals n dot p, in order to use the values in the current results, we will be getting that the formula becomes hash of m comma r dot p dot k plus r dot p equals hash of m comma r dot p dot n plus r dot p. But if we're using k equals n dot p and we have the formula k equals x dot p, then it's safe to assume that n is equal to x. So we replace hash of m comma r dot p dot k plus r dot p equals hash of m comma r dot p dot x plus r dot p. So we still have a long enough formula and we want to simplify a bit. Let's choose arbitrary values such as r equals, well, big R equals r dot p and s equals hash of m comma r dot p dot x plus r. So the formula that was hash of m comma r dot p dot k plus r dot p equals hash of m comma r dot p dot x plus r dot p becomes hash of m comma r dot k plus r equals s dot p. So remember here that we have public key, a variable r, a variable s, and a variable p. P being the base. We know the key and we know the base. So if we have the m, the r, and the s, we should be able to prove that we have the x without having to provide it and risk a third-party interception. And in this context, the m will be the message that we're trying to encrypt, and rs is basically the digital signature expressed in a key pair. So in order to have a better notion of what this looks like, let me provide you an example. Here I have a very small demonstration of a program using a package called novel-secp256k1. In it, basically, I'm preparing a message, a private key, a public key that I'm deriving from the private key, a signature for which I'm using the message and the private key, and verification for which I'm verifying through the signature, the message, and the public key. Notice I'm not providing the private key because we already have derived the public key from it. So in order to understand this code better, basically what we're trying to do here is ascertain that the private key is correct if we have the information given the signature, message, and the public key. I have looked into the code for this package and found the following that can help us describe it a bit better. First, the public key, as I said, is derived based on the private key, in which we're basically converted to a hexadecimal value or to raw bytes. Then for the private key, we're trying to multiply, which is where the dot, the point addition comes from. And also we're trying to do a scalar multiplication. So here the multiply function basically goes over preparing the scalar multiplication and also preparing a fake multiplication in order to ensure there are no interceptions in the values in case an attacker may use a side channel attack to read an energy expenditure in the computer. Now we want to prepare the signature by using the message and the private key. Message is expressed as a hash. So here we're going over variables q, r, and s, which goes over this function. So in this function we perform some hash calculations in order to be able to get a key, and then once we have it completed, we check if it's valid by checking if the value of the function is above 0 for the private key, but it doesn't go beyond what would be parameters in the curve, so that we get a key that is within the curve and then can be calculated using the point addition. So last but not least, we want to verify. For that, we are giving it the signature, the message, and the public key. Notice how we're using a multiply function, which is the one below, which basically goes over the same operations of point addition, and also a multiply unsafe, but for this we're using the public key. That means that basically we're going back to, instead of using the formula that includes the signature, we're using the base formula k equals x dot p. In order to actually having the public key as a hint, we prepare the perform the actual point addition. And that's what the multiply and save function performs here. And once the values are equal, as we check on res.x is equal to r, once these two values are equal, we know that we're having the right, the message has been signed correctly, and therefore we have the right private key. And that's how we get the true. So back to the presentation, we have the game CryptoKitties, which was a popular game where players could breed, buy, sell, and collect cats. And the breed is important part because we now can see that players can contribute to the game assets and what to do with within the game. It's based on blockchain technology using the Ethereum network, and it ensures that the creation, storage, trade, and sale of bred cats is secure and that the cats are unique. So let's look at what the blockchain could be involved in a possible future. Let's analyze the threats first. In theory, if we get quantum computers, these should be able to brute force problems faster than a regular supercomputer. That means that any kind of cryptography ciphering techniques, schemes, algorithms that we have would be useless. But before we actually get worried about this, we need to understand that the quantum computers are an infant technology, and it is even estimated that computers powerful enough to even be reliable wouldn't be available until an estimated guess of 2025. And thus, if everything goes correct and we are able to have the biggest companies such as Google develop their demonstrations further and expanding beyond their specific scenarios. And also, in getting ahead to this, we have quantum safe or post-quantum algorithms that are being developed to prevent quantum cracking. So let's look at some uses in the future. First, there is QTUM, which is a cryptocurrency that is utilizing quantum safe algorithms to prevent quantum attacks. Now, through the blockchain, we should be able to see more efficient supply chain management across all industries because the transparency of transactions would allow for a complete documented history of any product. We should also be able to see a better quality assurance and auditing because the accurate records and problems in manufacture would be found more easily, as well as intelligent contract execution, where smart contracts should be able to automatically manage contract obligations, expirations, renewals, and such. And because of this, we should have faster transactions and lower fees because we're eliminating the need for intermediaries. So these are my references, and that is the end of my presentation. Thank you all for watching and have a great day.